So the rate of a chemical reaction is how we measure how fast the reaction makes products or uses reactants, and those of course are related to each other. So we have some illustrations here. A reaction with a fast rate. So we have dark blue and red reacting to form green. And at the beginning, when we start the clock, all we have is the reactants. And this is showing like 15 seconds, 30 seconds, 45 seconds. And as we go through time, we get more and more of the product, less and less of the reactants, until here at 45 seconds, everything has reacted. So that would be a fast reaction, finished in 45 seconds. A fast rate. Here we have a slow rate. So we've got, I think that color is puce. Puce and blue making pink. And again, we're starting with just reactants, and we have the same time progression, but at 45 seconds, this one still has a whole bunch of reactants left because it was slow. Okay? So the reactants go away slower, the products appear slower. Any questions about that? So rate is how much a quantity changes in a given period of time. A sort of rate that we're more familiar with is the speed of a car. That's a rate. It's the distance traveled, usually in miles, in a given period of time. So the units are miles per hour. And the good news is we're not going to have any problems where trains leave Sacramento at 55 miles an hour traveling south, and then another train does something else. We don't do those. This is all where we talk about speed. So we can have an equation for this. Speed is the change in distance divided by the change in time. So delta is change in. Okay, and you should have learned that in Chem 1A. And it's always the final minus the initial. So if you're going forward, right, the final minus the initial, the distance traveled is positive. And the time is always going to be positive, right? When we measure the rate of a chemical reaction, we're going to look at the change in amounts of reactants or in the amounts of products divided by the time. So instead of measuring a distance, we're going to measure how much reactant disappeared or how much product was formed divided by the unit of time, and then we'll get a rate for the chemical reaction. So let's look at a gas phase reaction. This one is hydrogen reacting with iodine to make two. Hi! It's all caps. It's hi. Hi! It's such a cheerful molecule, right? Unfortunately, it's really bad to breathe. But anyway, it's high. So if we look at the change in the concentrations of the reactants, like hydrogen, we start out with a bunch of hydrogen, and then later we have less, right? If we take that small amount at the end and subtract the original amount, we get a negative number, right? The change in reactants is always going to be negative because they are going away. Reaction rates are positive by convention. It doesn't mean they had a convention about it, but it's just, it's common practice. We always have positive rates of reaction. So in order to define the rate in terms of the change in a reactant concentration, we have to throw a negative sign in there because we know that the change in hydrogen is going to be negative. It's the concentration at the end minus the concentration at the beginning. This is going to be a negative number. That negative sign cancels that out and makes it positive, divided by the change in time. We can also look at the rate in terms of the other reactant. Okay? We can look at the rate with respect to a product. The products are going to be created, and so their change is going to be positive. So we don't need a negative sign there. It's just going to be naturally positive. Stoichiometry also is going to affect the rate of the reaction compared to the rate of product formation, right? So we get 2 of these formed for every 1 hydrogen that reacts. This is going to be being created twice as fast as these guys are disappearing. But the reaction can only have one rate. We can't say, well, is this if you're talking about that, and is this if you're talking about that? No, it's one rate. And so we include the factor of 1/2 because of the stoichiometry. So the rate of the reaction is 1/2 the change in the product. And this 1/2 comes from that too. The HI, the high, increases at twice the rates. This is, again, see, I do this all the time. I just said most of this on this slide. I get ahead of myself. So in order to have a single rate, we have to define it with the coefficients. So because this has a coefficient of 2, then we put 1/2 in front of it. When we did the rate in terms of hydrogen or iodine, well, the coefficient isn't written there, but we understand it to be what? 1. Well, 1/1. We didn't write that because that doesn't do anything, okay? But it's 1 over the coefficient. Here we have a graph of concentrations versus time. And so this is our hydrogen concentration, and we see that it is going down, right? Because it's reacting. And this is our high concentration. Here the high is high, and initially the high was low. Sorry. So it's increasing, the concentration is increasing. The HI is increasing twice as fast as the H2 is decreasing because of the stoichiometry. We can look at an average rate of the reaction. Here, in terms of the hydrogen ion concentration, the rate is equal to -1 times the change in the hydrogen ion concentration divided by the change in time. So we're going to look at 2 different points in time. So we'll start with time 0 and 10 seconds. And so delta T is 10 minus 0, and so we've got a 10 in there. And the change in the hydrogen ion concentration is 0.819 minus 1, which gives us a negative number. We take this number, we divide it by that number, and then we've got this negative sign multiplied by -1, and so we get a positive rate. Any questions about that? And so we can look at the second point and the third point together and look at the change in time. Well, it's 10 seconds again because they set it up that way. They just measured it every 10 seconds. And look at the change in concentration. So at the end of that first one, it was 0.819, and now it's 0.670. You take this minus that, gives you negative 0.149. Divide by 10, multiply by -1, and the rate is 0.0149. The rate of the reaction is slower, right? As time goes on, as the reaction progresses, the rate will decrease. It's going to slow down. Because in order for things to react, there have to be reactants, right? And once everything reacts, what's the rate of the reaction? 0, because there's nothing to react anymore, right? So it's going to start at some number and it's going to decrease. Any questions? We can look at an instantaneous rate. When we looked at the average rate, we were looking at, say, this point and this point. And we're taking the concentration here minus the concentration there, the time here minus the time there, et cetera. But you can see, like in here, it's not a straight line, right? It's a curve. So the rate is actually changing in a nonlinear form as it's going along. So sometimes we might want to know, well, what's the instantaneous rate? Not between this and that point, but what was it at that instant? So then what you can do is you can draw a tangent to the line. So a tangent touches the line, in the curve, in one place and tries to be like equally spaced from the rest of it. I don't remember how they describe that in math. That was a long, long time ago. But you can Google tangent if you need help with that. You draw a tangent line, and then you're going to calculate the slope of the tangent line. The slope is the rise, the change in concentration, over the run, the change in time. That's rate. Change in concentration divided by change in time. If we do that for the hydrogen, we're going to find that this slope is negative. And when we take the change in concentration over the change in time, we have to multiply by -1 because it's a reactant, and again, we get a positive number. Okay? Any questions? So one of the homework problems gives you a curve like this, and it doesn't draw a tangent line for you. And it's going to ask you what the instantaneous rate is at a particular point. And you've got this on your phone or your computer, and you're like, someone asked me that this morning. What are we supposed to do here? I don't know what the publisher intended students to do, but what I figured out really works well. Take a screenshot of the graph, put it in Notability, draw a straight line on it. Then you can look at the points and figure out what the slope is. Okay? Questions? Mm-hmm.
What's Notability?
What's Notability? That's a good question. Notability is an app. So there's lots of different apps for tablets and phones that allow you to take notes, draw pictures, do things like that. So that's what Notability is. It's the one I use, so it's the only one I know about, actually. But bring it into some sort of an app. Actually, even the photo thing on an iPad or a phone will allow you to draw on it. You can do that and edit the photo. And so you can just do it that way too, but it's harder to draw the straight line. Any other questions? Oh, yeah, I'm talking about this one. Okay, so let's generalize what we've learned so far. Here's our generic reaction. A moles of A reacting with B moles of B, etc. So the lowercase letters are the coefficients, the capital letters are the chemical formulas. So we can define the rate in terms of the change in either reactant or the change in the products. And so we did that here. There's one rate for the reaction. These things are all going to be equal to each other. You usually don't know the changes for all of them. Usually you know the change for one, and you feel very fortunate that you know that much. But we would write the equation this way. For reactant, negative. 1 over the coefficient times the change in that concentration divided by the change in time. This is the same format, but it's a different coefficient. For the products, you don't have to put a plus there, but they did that just so that you would take notice that there's no minus sign there. 1 over the coefficient times the change in concentration over the change in time. Okay? So if we know the rate of change of one thing, like if we know the rate of change of A, we can take this part of the equation and set it equal to this part of the equation and calculate what the rate of change of D is, right? You can do that for any other substance in the reaction, but it doesn't tell you what's going to happen in the future. Well, what's it going to be doing 5 minutes from now? No clue. We can only talk about what is happening right now. Okay, so this is an example, and you see in your notes, you've got the question all written down, so you don't have to scribble that down real fast. I'm going to be writing here, and you've got space on your paper to also write. So I strongly encourage you to write it down with me, have your calculator, and check my calculations because I make mistakes. Okay, let's do this problem. Consider this balanced chemical equation. We've got H2O2 reacting with I- and H+ to form I3- and H2O. And it tells us that in the first 10 seconds, the concentration of I minus dropped from 1 molar to 0.868 molar, and they want us to calculate the average rate of the reaction in this time interval. So, we have learned that the rate is equal to, this is a reactant, right? So negative 1 over the coefficient. What's the coefficient on the H2O2? 1. Do you need to write that? No, we don't. Let's erase that. 1 over 1 times delta H2O2 divided by delta T. The brackets around H2O2 mean the concentration of that thing in moles per liter, in case you forgot. So in order to find the rate, we need the change in this concentration, and we need the change in time, and in that little sentence, they gave us the information we need. So the change in the H2O2 concentration is equal to the H2O2 concentration at the end, let's call that final, minus what it started at. So they say it went from 1 to 0.868. So it ended up at 0.868, and it started at 1. Calculator again.
Are we looking for the concentration of iodine or H2O2?
Thank you. See, I make mistakes. I wish I could say that I did that on purpose to see if you're paying attention. I didn't.
You could just lie to us.
I could lie to you, but I don't like lying.
But it
Changes because the coefficient is different.
Yeah, so we've got information about the iodide, and so we don't know anything about the H2O2. And so this is just what my husband calls a brain fart, right? I was just going with the first one because oftentimes it is the first one, but here it is not. The letters can get confusing. This is I minus, and this is I3 minus. So this is the product, and this is the reactant, and they're telling us about the I minus. So it is a reactant, but you can very easily get those mixed up. So delta T is 10 seconds because they told us that. So then we've got negative 1 over 3 times negative 0.132 divided by 10 seconds. And the calculator shows me 0044. And because I got the sig figs wrong yesterday, I remembered to pay attention to them today. We've got 3 sig figs and 3 sig figs. This should have 3, not 2. The book's going to put a 0 there. And the units would be molarity per second. So instead of miles per hour, we got molarity per second. Any questions? I would encourage you to, do that math on your calculator or one of the classroom calculators. Calculators are stupid in a way because they only do what you tell them to, not what you want them to, right? And they're different. And some of them you need to tell it differently than other ones. And so you want to find out that you're miscommunicating with the calculator during lecture, not when you look at the results of your exam, right?
I'm sorry, I wasn't thinking.
That's okay. Okay, that's the answer. The book gives it in scientific notation. Same thing. So determine the rate of change in the concentration of hydrogen during this time interval. Well, this is part B. Feel free to come up and have snacks or beverages or whatever. We know that the rate of this reaction is 0.00440 because we just calculated it. That's the rate. Now what they're asking us for is the rate of change of the hydrogen ion. Well, we can relate that to the rate, relate, whatever. So here we're talking about a reactant, so it's going to be negative. The coefficient's 2, so it's 1/2 times the change in the hydrogen ion concentration. It's a sad triangle. Divided by the change in time. So there will be a question like this on the exam, and we're going to do some things that are a lot more complicated after this, and you're going to get real comfortable with that, and then you're going to come back to do something simple, and you're going to go, what? What makes this confusing is, what are we solving for here? Are we solving for H+? Are we solving for T? No, we're solving for this whole messy thing, right? We want this whole thing. So we could rewrite that as this is equal to -1/2 times x, and we're solving for x. Because we're kind of trained that we're supposed to solve for one of the variables, not one divided by the other, right? So we're solving for x. Wording somehow. What about the rate of change of our I3 minus? It's going to equal the rate, right? We've done all this writing everything out. Let's just skip it this time, right? So the rate is going to equal, this is a product. So the change in this over the change in time. Well, that's the thing that we're trying to find, right? So delta I3 minus divided by delta T is equal to the rate, which is 0.00440 molarity per second. Yes?
Why is there that extra 0 after the 4s again?
There's an extra 0 after the 4s because of significant figures. So, if we go back to the first question, it gave us 10 seconds. These are zeros at the end of a number, and if there's a decimal point that's written anywhere, those are counted. So this means 10.0 seconds means it's between 9.9 and 10.1. Pretty tight window. And these, when we subtract these, we ended up with 3 decimal places, which is 3 significant figures. So we took that number and divided it by this number. They each had 3 significant figures. So the answer should have 3 significant figures. This number has a trailing 0 and leading zeros. It's the zeros that mess everybody up. So numbers that are written before the non-zero digits are not considered significant figures. They are there to hold the decimal place. It doesn't mean they aren't important. They are important, but they're not a sig fig, okay? If we left these off, then we'd be going like, well, how many spaces are in there? Let's just take those out and see what happens. You left some space. Did you mean there to be 1 0 in there, 2 zeros? You know, how far over is that? We can't tell. We need those zeros. but they don't reflect how precisely something was measured. So we don't count those, we start counting with the 4 and the 4. The calculator didn't give us the next digit because the calculator is not in the habit of putting a whole bunch of zeros at the end just for fun. And so we know that it should have 3 significant figures, and so we add the 0 in there. Do you remember hearing about that stuff?
I did.
Okay, yeah. Sig figs are something that, So, in my Chem 1A lectures, there's one just about sig figs. So you might want to refresh on that one. And, anybody else who struggled with sig figs in Chem 1A might want to refresh. Any other questions? Yeah.
So this is all the instantaneous rate of change at 10 seconds for each of these chemicals?
This is actually the average rate over the time interval.
Okay.
Yeah. Because we're looking at the period between 0 and 10 in the first 10 seconds. So it's the average over the time period. We can't know the instantaneous because it's changing, and we don't have that information. In order to find the instantaneous, we would have to graph this and find the slope of the tangent at the point we were interested in.
So this would be derived with that.
Basically, yeah. And, with computers and stuff, you can put the stuff in there and it'll do a best fit line for you, and then you can ask it what the tangent is at that line, and it'll tell you and give you the slope. But we're not going to learn how to do that because we're only going to mess with that in this very beginning part. Any other questions? This is a conceptual connection problem. So this means we're just talking about the concepts as opposed to like solving mathematical problems. So here we have a reaction with A reacting with 2B, going to C. Got a given set of conditions. It doesn't matter what they are. The initial rate of the reaction is 0.1 molarity per second. And this is asking us, what is the rate of change of B under the same conditions? So there's 2 ways you can approach this. You can think about it, or you can rough out some equations for it. I like math. I prefer to write the equations. I can think about it, but I get it backwards a lot. So if we're thinking about this, the rate of the reaction is 0.1. Is B changing faster or slower than the overall rate? Faster. A, the change in A over change in time with a negative would be equal to this. This has a coefficient, right? When we use up one A, we make 2 B's. So for every A that gets used up, we use up 2 B's. So we're using those up twice as fast. So we can think about it and say, oh, well, it's twice 0.1, and because it's a reactant, it's going to be negative. I don't think that works really great, because I got it backwards yesterday. So this is what I would do. We know that the rate is 0.100. Oh, yeah, there's the answer. We'll just ignore that. I can do this. I think I can do this. I did it. That's the rate. How is the rate related to the change in B? It's a reactant, so it's negative. 1/2 delta B over delta T. So this is equal to half of that, right? So, and there's a negative here. So this must be twice as big and negative. And you can also do that by, let's divide both sides by -1/2. I don't know, maybe no, let's not do that. That's too confusing. We're going to multiply by 2 on both sides. Ugh, so quit jumping around. Not you, my screen's jumping around. And then we'll move this negative to the other side. And that's one of those situations where the algebra is actually really simple, and yet it's hecka confusing. Because your mind wants to take this, and 1/2 of this is equal to that, but that's not what it's saying. So just watch out for those. Any questions? Okay, so let's talk about how you would measure a reaction rate. In order to do that, you need to be able to measure the concentration of at least one reactant or one product in the mixture. And you need to monitor that as a function of time. So there's 2 ways to approach the problem, and they will be different based on how fast the reaction is going. So if you have a reaction that's going very quickly, you want to be able to monitor continuously, because the rate of the reaction is changing quickly, right? If you have a slow reaction, like 2 weeks, right? That's a slow reaction. It's going to take 2 weeks for this to happen. Do we need to monitor every half a second for 2 weeks? No, we could probably do like every 6 hours or something. It's going to change a little bit, but not too much, right? So we would use different methods of sampling based on how fast the reaction is. How do we measure things, concentrations, continuously? I am not going to test you on these methods, just so you can, untense. Polarimetry is a method that looks at the rotation of plane polarized light. Like, what does this have to do with a concentration? There are a lot of optically active compounds. Most of them are organic in nature or biochemical, like sugars. And so there's a D and an L version. And one of it rotates plane polarized light to the right, and one rotates it to the left. And how much it rotates depends on the concentration of the sugar. So that's one way you can measure a concentration, is looking at the rotation of plane polarized light. Now, is that one that has like big general application? No, no, it doesn't, but it's kind of cool. If you have a reaction that's occurring as a gas, the reactants are gases and the products are gases, you could measure the total pressure of the reaction chamber, because it's going to be related to the partial pressures of the gases. So here, if we have 2 moles of N2O, and that's going to make 2 moles of N2 and 1 mole of O2. When we get to the product, we're going to have 3 moles of gas instead of 2. And so there's a little algebra you'd have to do in there, but you can figure out from the change in pressure how far the reaction went. Another way is spectroscopy. This is one that we're actually going to do in an experiment. So this uses the absorbance of light. So many substances will absorb light, even in solution. Like this, like, Diet Dr. Pepper, that's absorbing a lot of light, right? It's just almost nothing going through. But you can measure how much light is absorbed, and it's related to the concentration. And this is a sketch of how you would do that. So you have a light source, and you take just part of that, and then you run it through a prism to separate it into the different wavelengths. And the monochromator is another slit, basically, and here that slit is only letting the green light pass through. So the green light goes through the sample, and then we have a detector. And, it might absorb half of the light, or a quarter of the light, or whatever. The detector will tell you that. And that's connected to a computer, and you can measure that. So you can measure continuously as the absorption of this is increasing or decreasing. It's related to the concentration. Okay, any questions about that? For periodic sampling, you need to take a part of the reaction mixture out and test it. And that part that you take out is called an aliquot. So I'm not going to test you on that word, but it's going to show up different places. And you're like, what the? It's not like a tourniquet or anything. It's aliquot. It's just a sample. So you take samples off at particular times, and then you test them. It's called quantitative analysis. How much quantity of this thing is in here? Common techniques include titration, gravimetric analysis, and chromatography. Now, I think you all know what titration is, right?
Yeah.
Hopefully I didn't, trigger anybody. Gravimetric analysis is using mass. So one way of doing gravimetric analysis is you can add something that's going to precipitate the thing you're interested in. You filter that out, you dry it, you weigh how much there was, and then you can tell what the concentration was. That one can get really tedious. Well, titration is by nature tedious. Or a gas chromatographer. What this says. So the neat thing about gas chromatography is you can measure concentrations of more than one thing in the mixture. And we have a grass chromatograph.
Yeah.
I don't know. We have one of these in the back room. And if you do the certificate program, the Chem 20 class, you actually get to use it. Very cool. Anyway, so you have a gas. It's usually something like nitrogen or helium that's not very reactive. And this gas is flowing through a column. It's a teeny, teeny, tiny tube that has a special coating on the inside. So the gas goes through here. It comes through a detector. And when it's just that carrier gas, the detector just says nothing. Then you put your aliquot, your sample, into the injection port. And in this example, it looks like it has two different things in it. So those two substances come in here. One of them is going to be more attracted to the coating on the inside of the column than the other. And so it's going to slow down. It's like, oh, I like this. I don't want to go too fast. I really like you. And the other one's like, I'm going straight through, right? So one comes through before the other one. And so that you can detect them separately. It's very cool. This is an extremely useful technique. Yeah, polarimetry, not so much.